3, 2, 1, let's go. All right, well, what do we have here? We've got Chapter 6. We got Gram-Schmidt, and I'm excited. I gotta tell you, I'm very excited. This is good stuff we're gonna do today. And I've got pictures that I even made for you. Okay, you're gonna get dazzled by some graphics today. So, all right. So the goal for today is to really talk about geometry, I guess, in a sense. So we already kind of touched on the structure of Rn. As a vector space, right? It's got scaling and adding. It also had some other operations associated with it. So if you let your mind float back, it's been a while. It does have a multiplication, but it's not a traditional multiplication, because note, you take two elements out of Rn, and you sum up their entries multiplied together. Now this is known as the dot product, and we used this and talked about the ins and outs and what have yous about it. So specifically, let's remind ourselves some properties that we know about this. It's commutative, so the dot product of x with y is the dot product of y with x. The dot product of x with itself is equal to 0 only if x itself was 0. Remember that if I scale the dot product, I can put the scalar wherever I want. And the dot product of a sum is sum of the dot products. Now, those last two notes there's another way of looking at them, and that's a way that we want to really stress. We have some new terminology and language, so we're revisiting some stuff here. That last 2 points actually tells us that the dot product induces a linear function from Rn to n, where, right, you lock down a v and then you take a dot product. Right, note it's linear, because if you were to scale the x, I could pull the scalar out, and if you were to add some inputs, x plus y, well, the dot product goes across the way you want it to. Oh, nice. So, technically, some deep lore math here for you. What this is saying is that the dot product is actually what's known as a bilinear form. And, yeah, that sounds like you're doing something really serious. It's just the dot product. That's all it is. So that's interesting. That's recontextualizing something we've already talked about. Nice. And, oh boy, here'd be a really fun... Ooh, that would be a really nasty final question. Prove that every linear mapping from Rn to R is a dot product. Ooh, that'd be a brutal problem. I gotta think more on that. I literally just thought of that. Because it is true, by the way, actually, every linear mapping from Rn to R is actually a dot product in the skies. That's known as the Reese representation theorem. I'm going off the deep end. Let's keep reminding ourselves of things we actually know. Alright, so another thing that we were talking about associated with this, letting your mind flip back, this is literally week 1 stuff, was this idea of length, right? So you can compute the length of a vector in Rn by taking the square root of the sum of the squares of the entries. Right, and we went with this as the formula because for R2, this is just the Pythagorean theorem in disguise. Seemed pretty reasonable. And remind ourselves a couple of things about the length is true. So the norm of x is greater than or equal to 0. It's equal to 0 precisely if x is the 0 vector. If you scale your vector x by alpha, you can pull out your alpha's its absolute value. The triangle inequality holds, which is just saying that, well, x plus y and x and y themselves, they form a triangle when you draw them out in R2, and this is just saying that the shortest distance between 2 points is a straight line. That's literally that, formalized very precisely. And remember that the way we proved that was based on the fact that the length has some nice connections to the dot product. Specifically, the length squared is x dotted with itself, and with some manipulations, x plus y squared turns out to split like this, so quite nicely. Alright, so let's just revisiting some things. It's been a while since we talked or played around with these things, and today we're going to kind of combine all of this stuff we talked about at the beginning of the class with some of the new things we've been talking about. Right, so we kind of already touched on it, though. The dot product we can view as a linear mapping. Nice. So let's keep going. All right. So speaking of R2, there's something that we kind of vaguely mentioned, but I said let's pause on that and we're going to revisit it, and here we go. If I take two elements in R2, I can draw this picture right here. Note that I can formulate this angle between x and y. So here I have a triangle, not necessarily a right triangle. It's got side x, side y, and the other side has to be x minus y. I have an angle, and of course you remember the law of cosines, because, I mean, who doesn't have this at the ready? Right, so law of cosines, if you don't remember, tells you that the side, the angle that it is facing, the side squared, so its length squared, has to be the length squared of x plus the length squared of y, so almost the Pythagorean theorem, but then there is sort of this defect term that shows up, minus twice the length of x and y times cosine of the angle. And if you don't remember this, and you need to derive it on the fly, it's not too bad. Remember that every triangle, there is a right triangle hiding in here, so specifically, if you were to pick this side and shoot a line here and make the right triangle, would be somewhere down over here, it'd be pretty tight. But you can make a right triangle, you can cut the triangle in half, make two right triangles, and then from there you can use the Pythagorean theorem and work this out. Now note, as we just discussed, x minus y squared, the norm of that can be written in terms of dot products. And, oh hey, if I match this with this, I find that the dot product actually can be rewritten in terms of the norm of x times the norm of y times cosine of the angle between them. That's real interesting. Now, this, of course, right here isn't a proof of anything. This is just intuition based off of geometry, right? And as I've repeatedly said, Karl Weierstrass, the greatest mathematician ever, he finally hit the point and said geometry is a load of garbage. So let's formalize this geometric intuition to some more precise mathematics. Now recall that for two vectors out of Rn, we have the Cauchy-Schwarz inequality, which tells us that the absolute value of the dot product is no bigger than the product of their norms. Another way of viewing that is that the dot product has to live between the product of the norms and the negative of the product of the norms. So it's stuck inside of this symmetric interval, and that means I can find always a unique theta so that that equation has to hold, right? Cosine from 0 to pi will spit out all of its values of -1 to 1. So there has to be an angle so that multiplying cosine phi times the norm of x times the norm of y coincides with the dot product, since the dot product lives in that interval. Alright. Cool. Alright, so that's how you would formally define what the angle between two vectors would be. Okay, right, so note here, this is an actual very precise mathematical definition based off of things that we've actually proven, and we got to it by our geometric intuition. Alright, so there was a difference there. We used our intuition from a picture to help us come up with a definition. Okay. And we've kind of already talked about this because perpendicular would mean a right angle, which would mean a theta equal to pi over 2, and that can only ever happen if the dot product was 0. So we did kind of briefly touch on this. I let this one slip a couple of times in class, that the dot product equaling 0 happens exactly when the vectors are perpendicular. But now we have it very precisely stated and a deep geometric intuition as to why that would even be true in the first place. Alright. Nice. Now, on the flip side, perpendicular means the dot product is equal to 0. The other direction would be parallel, which would be if the angle was 0 or the angle was pi. Right, because if the angle was 0, that would mean that they're facing in the same direction. And if the angle was pi, that would mean they would be in opposite directions of each other. Equivalently, that is when the dot product actually equals the product of the norms in absolute value. Right, the norms are non-negative things. The dot product can be negative, as we're going to see today. But yeah, so we've got that. Now note something about parallel vectors. If we're thinking about what they're going to be, either in the same direction or in the opposite direction, Well, any vector is parallel to itself, since the dot product is equal to the norm squared. And any vector is parallel to x, dot product anything with x. Now remember, dot product is a linear mapping in disguise. If you plug in a 0, we know that if you feed 0 into a linear mapping, you get 0. So, got you there. And the norm of 0 being 0, so that works. So any vector is parallel to itself, and it's parallel to 0. So where am I going with this? Well, I'm going to prove that parallel is precisely equivalent to linear dependence, right? So note, parallel we have described in terms of an angle, and linear independence, so note the distinctness, because we know anything's parallel to itself, and non-zero for the y, because we know anything's parallel to 0, so it's not interesting. Alright, so here we go. We're going to prove now parallel, a geometric idea that we've made very precise, is equivalent to the idea of linear dependence. Alright, so like I said, this whole chapter here is kind of like just coalescing everything we've talked about into just one beautiful thing, right? Because we started off, dealing with Rn and really having, very concrete workings with that. Then we went off into the abstract world of vector spaces, and now we're kind of pulling it back and interweaving. I'm doing a lot of hand motions that you cannot see. I'm the master of mysticism, or Dr. Strange, whatever, who cares. Bandy Dance, Scramble Stanch. Alright. I'm having a good time. Alright, so suppose two vectors are parallel. What does that mean? That means that the absolute value of the dot product coincides with the product of the norms. Alright. Now, I'm going to let lambda equal something. Here's a classic math proof of, I'm just going to do something. I'm not telling you why right now, other than this is the exact right thing that we're going to need in a little bit. Classic math proof. Now, if we were doing this in class on the chalkboard, I would be like, okay, let's make the next step and then figure out what lambda needs to be. Because, what do I want? I want to prove that x and y are linearly independent, so obviously I want to find a scalar so that x is equal to lambda scaled by it. A y scaled by lambda. Alright, now note something. The dot product squared has to be the norm squared. Then, bunch of equations here. Right, I'm going to leave that up there for a little bit, let you really digest what's going on. So note what I did. I looked at x minus lambda y quantity squared. This move that I'm pulling right here, this is a big move. This move is used a lot when you're dealing with Rn. You look at x minus lambda y norm squared. Right, recall that I know what that's equal to in terms of a dot product. It works out like this. Lambda squared gets pulled out here. So, how did I choose this lambda? Why did I even pick this lambda to begin with? Well, the way I did it, of course, was I started here, got here, and then I went, you know what, I want this to equal 0. And what is this? Oh, that's a quadratic equation in terms of lambda, so I literally solved for when lambda needs to equal 0, and hey, it's equal to this. And here, note that we are explicitly using the assumption that y is non-zero. Alright, so you plug that in, and you can work out the details. It equals 0. I know it has to work because I figured out what lambda was by the quadratic equation. It's literally how I did this. I knew, I didn't quite remember the full details on the proof of this, other than I'm like, well, I need x to be a multiple of y, so let me set that up, and then I squared it, looked at the norm, and then I was like, oh, that's right, then you do the quadratic equation to figure out lambda, so... That is a very frequently used move, I really have to say. But yeah, so boom. They're linearly dependent. One's a scalar multiple of the other. Yeah, there you go. Nice. Okay, so parallel, which we precisely defined, right, based on our geometric intuition, we have now proven that it is that it implies a linear dependence. Okay, so let's go in reverse. Suppose that you had linearly dependent set of vectors there. So that means one is a scalar multiple of the other. And what do we need to show? We need to show parallel, which means we need to show the absolute value of the dot products is the product of the norms. And so in the first case, We know y is alpha x, and then just do a bunch of dot product arithmetic there, move everything around. Right, noting that dot product of x with itself gives you its norm squared. Norm squared is just two norms, so sneak one of the alphas in, that turns it into a y, and bing, you're done. And in the other case, you get the exact same conclusion, so nothing too nuts there. Alright, so hey, there we go. Linear dependent vectors has to be parallel, and vice versa. So that's really nice, and that matches, again, the geometric intuition from R2, but now we've got it on rigorous standing, right? We've taken these geometric ideas and we've made them very precise, and we've got nice proofs of them, and we're seeing them bleed and intermix with all of that linear algebra stuff we introduced. So, yeah, good stuff. Alright, so let's go back to R2. Let's draw another picture. Ooh, oh, look at this in color. It's beautiful. Alright, so if I take two vectors, x and y, I can arrange them as so, where I took my vector x and my vector y, and I connected x to y, and note that x minus p forms a nice little right triangle. So if I think about this in terms of parallel and perpendicular, in R2, no matter how you draw your vectors x and y, you can always rotate them, move it around, just change the picture so that you can make this vector p and this vector x minus p. So in R2, our geometric intuition, my pictorial intuition, is that I can always find a vector p parallel to y with the property that x minus p is perpendicular to y as well. Okay. So that's the geometric intuition. So what's the actual precise mathematics? Okay, I need to prove that for any elements x and y out of Rn, right, I'm going to do this for even more than R2, Rn, that I can find a vector p out of Rn with the properties that it's parallel to y, and x minus it is perpendicular to y. And it turns out there's a nice, beautiful formula that if you've taken Calc 3, you already know what this is. This nice, beautiful formula right here. So you take two vectors, x and y, where one of them is non-zero. Specifically, we're going to have y be non-zero. If one of them is zero, there's nothing to do. There's nothing interesting going on here. Then the vector that's formed by scaling y by x dot y divided by y dot y. So note, dot product is a scalar. Dot product is a scalar. This is a scalar. X vector minus dot product of x and y divided by dot product of y and y. That is a scalar. Vector minus scalar times vector. Right. So keep that stuff in mind. Right. So you want to be really careful when you're doing linear algebra like this, keeping track of sort of the types that are flying around, what are scalars, what are vectors, especially when we start intermingling with like dot products and stuff like that. The equations, you can quickly start going like, oh, cancel the v, y's or something. You're like, no, can't do that. One's a vector, one's a scalar, not allowed. Right, so keep that in mind. Anyway, so the claim here is that this has to be parallel to y, and this has to be perpendicular. So, for the parallel part, I just directly did it. I mean, we can see it, right? They're definitely dependent. One's a scalar multiple of the other, so. But it is worth noting, right? And again, I want to play around with these dot products and show off the moves, right? That the absolute value of that is equal to this. Oh, that's right, because I'm, right, I paused. See, I was pausing because I was like, wait, this equation doesn't make any sense, right? Because I'm missing that y. See? Do it live, man. When you mess up, everybody learns. I was just leaning back in the chair. I actually had to freaking, my old man body. Alright, let me get the very engaging part of the video right now. Alright, yeah, okay, now that's correct. Now this is a vector. Before it was a number dotted with a vector. That's bogus. That's not a real thing. Alright, and the same thing over here. I've got that term's not good. I gotta fix that one as well. So let me go in there and get that. Yeah. You're sitting at home. Well, I mean, if you're smart, you got this on like a 1.5 speed or something like that, so. Flying right through this. Oh, Joof, what's going on there? Oh, God. Oh, no. Yeah, what is going... Oh, okay, I see. I see what's going wrong. I put the slash left parentheses in the wrong spot. So that's the one thing that, there we go. Okay, now it's good. There, yeah. Nah, now we're good. Okay, we're all good. Okay, all right. Okay, let's pull this apart here. Okay, so now we've got this vector dotted with this one. Okay, so this is a scalar, which means we can pull that out. Then we have y dotted with y. That allows me to cancel the y dotted with y, leaving me with x dotted with y. That was my initial hesitation. Like, wait, that doesn't give you x dot y. What's going on? But anyway, so I guess that's that. Now, y dot y is the norm of y squared. So we have that, and then I've got two norms of y squareds, so I pull them apart. One of them gets on its own, the other one I sneak in these terms. Right, no, y dot y is the norm of y, so you can sneak it into the norm there. See, now I'm regretting that I did. I should have just been like, it's a scalar multiple, they're dependent, we're good, moving on. But anyway. They're parallel, as we see right there. And for perpendicular, you do the dot product. Note that when you do the dot product out, you get x, y dotted with x right there. Here we get the y dotted with y, which would then cancel the y dotted with y right there. And you'll be left over with that, but as we know, these are the same thing, so their difference would give us 0. All right. Boom. So there we go. So for any two vectors, x and y out of Rn, where y is not equal to 0, I can always concoct a vector parallel to y, so this one right there, so that x minus it is also perpendicular to y. Right? This is known as the projection of a vector onto another one. If you've taken Calc 3, you've seen these. It's a very useful tool, and it's going to be an incredibly useful tool for us. And here's why. So let's take a basis for R2. Note that these elements are not perpendicular, or orthogonal, the other word for it, right, because the dot product is non-zero. But note, I just learned that if I take a vector, subtract the vector dotted with the other vector, divided by the norm of the vector, times that vector, that will give me something that's perpendicular to this vector 1, 1. Right? So I'm just plugging in that formula, the projection of a vector into another one that I just talked about. Note that this piece right here is clearly perpendicular to 1, 1, right? If you take the dot product of the two, you'll get negative 1/2 plus 1/2. They would knock each other out. And furthermore, this then is still a basis for R2, right? You could verify that they're linearly independent, right? Clearly you can't scale this one to that one. Now, by basis here, I turned it into a basis comprised of perpendicular vectors, right? And draw this out in R2, what this looks like, right? This was, kind of a nice little sharp triangle, but this one here gives you this nice right angle going on there. Nice. Okay. So, this that we just saw in R2, taking a set of vectors and turning them into a orthogonal set. That might be what the Gram-Schmidt process is. So we want to do what I just did in R2 and Rn. So, specifically, given a basis, I want to create a basis that involves only perpendicular vectors. Okay. So a subset is said to be orthogonal if the individual elements are perpendicular or orthogonal to each other. I was avoiding using the word orthogonal for a moment, and well, we're really going to get into why I'm avoiding that word. I like perpendicular. This is one of those cases where the fancy math word I don't like. I like the perpendicular. It's a clear picture in your head. I mean, I know I should be using orthogonal. It's the fancy word everyone uses. Right? I get all thin out of shape about 1 to 1 and on 2. Like, that's baby words, right? But orthogonal to me is, I got a story about why I'm not a fan of that word, but I'll try to use it. It's the thing. You don't call these a perpendicular set of vectors, you call them an orthogonal set, so. Anyway. So, right, they're perpendicular for distinct terms. Let's prove something with them. So it turns out this result here is going to be one that's going to be very useful for us. Let's say we have an orthogonal set of vectors and any set of scalars, and I've got alpha sub n there. It should be sub m, because we don't necessarily need to have the same number of things that we do in n. We can have a subset that's smaller or bigger. Alright, so if it's orthogonal, then it turns out that the norm of the sum of the vectors scaled by alpha, so that linear combination, the norm squared turns out to just be kind of what you would want it to be, right? You kind of just pull everything inside of the sigma, right? Now note something. If I look at this in R2, this is x plus y squared is equal to x squared plus y squared for perpendicular x and y. Now, if you think about the picture of what x, y, and x plus y are, that's a triangle. That's a right triangle. A squared plus b squared is c squared. This is literally the Pythagorean theorem. We are going to prove the Pythagorean theorem right now. And there it is. So I didn't need. I didn't intend for that. But I had pauses in there. I guess. Oops. I'm keeping this in. I'm just gonna. This is my proof. I'm just gonna. Oh man! Speaking of giving terrible talks at a conference, that'd be great. Oh my god, I would love that if I ever did that at a conference. Where just put up a slide and just have a bunch of equations, just start laughing. Oh man. All right. Well, yeah, do you get it? It's a good proof. All right, so let's break it down. What's going on here? Okay, so you start with the norm squared. Okay, note that's the dot product of the things, and note I changed the indice here for a very good reason. Right, indices, they don't particularly matter, but we really want to be careful what's going on here. So now, remember, dot products are linear. So here we have this dotted with that, which really means that I can pull out the summation and I can pull out the scalars. So this dotted with that, dot product is a linear process. So it really is just sum up the scales of the individual x v sub k's dotted with this. And then we can apply that same logic. Dot products are linear, so I can pull out the summations and the scalings. Okay, so we have summation of scaling of dot products. Now these dot products, by assumption, are equal to 0 when j and k are different, and when j and k are the same, we just get the norm of vk. So this term on the inside will just turn into alpha k times the norm of v sub k, and there we go. Beautiful. So that's a nice slick little proof. Alright, kind of nice. Right, and note, I used a reinterpretation of dot products, right? We could have proven this a little bit earlier on, but we would have had to been really careful about this particular move here in the beginning. Alright, but now we know we can do this by the linearity that we just discussed that dot products possess. So they do respect scaling and addition in the way you would want them to. Beautiful. Okay. So, for what we're going to accomplish here, we're going to want this result, because equipped with this, I can now prove something about orthogonal sets. If I have a set of vectors that are all non-zero, and I really want to stress this, they are all non-zero. This is a key ingredient in the proof. Then this set of vectors is not only distinct, they are linearly independent. So before, when I said you have an orthogonal set, we now know that that m needs to be less than or equal to n. So you actually can't have more orthogonal vectors than you do vectors that form a basis for Rn. Right, and that isn't too surprising if you start thinking about it. Just even think in R2. Pick two vectors that are orthogonal. Find a third one that's orthogonal to the other two. Good luck. Alright, that's not 0. If it's 0, it's cheating. Right? Okay, so let's do this proof. So the first thing I want to do is verify the distinctness of it all. Okay, so let's say you've got v sub j is equal to v sub k, and you've got different indices. So let's suppose that it was not distinct. Well, the orthogonality would ensure then that that dot product would have to be 0, but that dot product is v sub k dot of itself, which is the norm of v sub k squared, but that would tell me that v sub k is 0, which contradicts my assumption that everything is non-zero. So it's got to be distinct. So there actually has to be m elements in this list, so it's a proper listing. There's no repetition. Alright, now let's do linear independence. So what do? We do what we've been doing. You scale them up, set it equal to 0, and we got to prove all those scalars are 0. Alright, well, hey, I just proved that thing that said if you take the norm of something squared, you can pull it in, the Pythagorean theorem. So we know that the norm of the 0 vector is 0, so the norm of this linear combo squared there can then pull up like this. So now we have a summation of real numbers equaling 0, but by assumption, we know all of those norms are strictly greater than 0. They're strictly positive. And the only way we have this summation of stuff equaling 0, and the v sub k terms all being strictly positive, all of those alpha k's have to be 0. Otherwise, that summation is not equal to 0. So it's got to be that all the scalars are equal to 0. So it's got to be that we're nice and linearly independent. Beautiful. All right. So equipped to follow that, we can now officially prove the Gram-Schmidt process. So the Gram-Schmidt process says the following. Let's say you have distinct and linearly independent vectors, R sub m. So m in this case, as we now know, would have to be less than n, right? Because by dimension, there can't be more linearly independent vectors than there is the dimension of Rn, which would be n. So if you give me any collection of distinct linearly independent vectors, I can find a set of orthogonal vectors, non-zero, with the property that the span of my linearly independent sets coincides with the span of the vectors w1 to wn. So note, it's actually something a lot stronger than our original goal. Our original goal was just, well, if I have a basis, can I turn it into a collection of vectors that are orthogonal and also a basis? Right, this says you can actually do one better. If you have subspaces that you're interested in, you can form orthogonal bases for those based off of any basis you have. So this is actually saying a little bit something more than our original goal, which is quite nice. All right, now, so before we actually prove this, and the proof of this actually is surprisingly easy. So it's worth noting that it's named after two mathematicians, Gram and Schmidt, obviously. Although apparently, according to the history books, Laplace apparently already knew this, but didn't get any credit for it. So the Gram-Schmidt process. So Schmidt shows up a bit in linear algebra. If you get into some deep lore linear algebra, you're going to see his name quite a bit. Schmidt was in Germany at not a good time in the history of Germany. So he was tasked to deal with the Jewish problem. And apparently he was, quote, bad at it, but apparently he was also still like a Hitler superfan. So, I don't know. So Schmidt's a little problematic, I guess. His Wikipedia page just that doesn't really paint a good picture about this guy, but go ahead and look that up. Gram, on the other hand, this is the only time Gram shows up. Gram apparently did something with the Riemann zeta function at some point. Who knows? But the best part about Gram, this is the all-time greatest death in mathematics, I gotta say. So there's a lot of crazy deaths that have happened in mathematics, just randomly drowning, which is what Yuri Zhonded dying somewhere in World War II. A bunch of mathematicians said that one happened to him. Galois went out in a duel. Great way to go. But Gram's got them all beat. Gram's got the best death a mathematician has ever had. He got hit by a bicycle. And he died. That's, of all the ways to go out. I love that's like his Wikipedia page has like nothing other than like, yeah, by the way, bicycle got him. Anyway, all right. So let's do this proof. So, like I said, this proof is actually kind of shockingly easy. So the statement here, you might immediately kind of think like, oh, this is going to be a gross proof. It's not. It's really slick and kind of nice. So the trick is to do it inductively, though. All right. So let's do it inductively. So, indeed, just said W1 equal to X1. Well, X1 is coming out of a linearly independent set, so it has to be non-zero. So W1 is non-zero. A set that only has one thing in it has to be orthogonal by vacuously true, because there aren't two elements you can pick, so it's just automatically orthogonal. And the spans have to line up. So, n equals 1, base case. Boom, nailed it. All right, well, inductive hypothesis. Suppose that we've constructed an orthogonal set that has the desired properties, but I haven't quite reached M. Not M there, I want M. You know, I spent so much time on these damn slides, you know, and I do a little dry run to make sure everything's good, and every time I go through it, I still find you'll never be perfect. Yeah. Not too bad. Not the worst, right? Any mathematical thing you write, there's always something wrong with it. Even papers, that's even worse. In my field, there's a very famous paper, and it has this counterexample to this like reasonable sounding theorem. And when I was in grad school and I was studying this paper, I was looking at it and I'm like, wait. That's not a counterexample at all. That doesn't do anything. And I was at a conference, and the author of the paper was there, and I went up to him and like, hey, I was reading that paper, and that counterexample, that isn't right. And he followed that up with just, oh yeah, I know. Everyone knows. And I was like, what do you mean everyone knows? Everyone cites your paper and says it's the counterexample. And it's not. Like, man. And it's still not been solved as far as I know, or it might be hiding in some other paper somewhere, but like, the thing everybody references is this guy's paper, and it's like, not true. And he doesn't care. But he's like, yeah, of course it's not. Anyway. Okay, well, so what do we need to do? So we just need to show that we can extend it to p plus 1. Alright, so we proved it for the base case, assume it's good for p, and that will show it's true for p plus 1. Okay, so what do we need to do? Well, we just need to find a vector, w sub p1, so that when I add it to my already orthogonal set, I keep being orthogonal. It's got to be non-zero. We need that. And then we got to show that the spans still line up. So let's do it. Now, what's my WP sub 1 going to be? Well, it's going to hopefully look super familiar, right? Because this term right here, we've already encountered that, right? We know that this is going to formulate something that's perpendicular. Oh. So I claim this is the desired extension for my set W. So the first thing to do is to verify that it is indeed non-zero. Right, and this kind of is a little non-trivial, right? This at first glance is like, oh yeah, why? Well, how do we know that this has to be non-zero? Well, if it was 0, that would mean x sub p would live in the span of W1 to WP. But no, we've assumed that that is the span of x1 to xp. That would contradict that we had a linearly independent set. Ooh, look at that. That's nice. That's a slick little thing. Gram, you done it again. This guy knows what's up. I'm down. Ugh, those bicycles. Alright, so, indeed, we have to have our W sub P1 is non-zero. Alright, now what? Okay, well, next we want to show that adding this to the set of w's does not ruin the orthogonality of it all. Now, so that means that all we need to do is verify that the dot product of w sub p 1 plus 1 dotted with w sub j, where j is an indice other than p plus 1, indeed is equal to 0, right? So for any other indices, we know the dot product will be 0, right? So for example, if we did wj dot over wk, we know that that will equal 0 for all j not equal to k. And of course, here we want to stress that the k is between 1 and p as well, which is what's going on in the summation right here. So we do the dot product, it distributes across. Now in here, we know that, hey, we have perpendicularities, so they will delete out. Hey, we got a nice cancellation, and hey, we get those canceling out. So, hey, that looks virtually identical to the thing we just did before. Okay, so w sub p plus 1 is orthogonal to everything on the list previously to it. Everything in that list was orthogonal to begin with, so boom, that whole set is orthogonal. Nice. Pretty neat. So, even though it had this, like summation thing going on there, when you dotted it, it just boop, boop, disappears. Right, and here, hopefully, you're really starting to notice that this is why people work with orthogonality a lot. Because you can have summations flying all over the place, and then you just go like, well, then we do the dot product, and everything's gone, and the calculations are nice. So it's a powerful tool. Alright, cool. So what's left? Well, now we just need to prove that the spans do what we claimed they were going to do. Okay, so note that x sub p, if I rewrite the definition of w sub p, hey, that thing right there needs to be in the span of w1 to wp, right? Because it's a linear combo of things from that list. Now, that means that the span of x1 to x sub p plus 1, x1 to xn is in the span of w1 to x1 to xp is in the span of w1 to wp, and we just proved that x sub p is in the span of this bigger set, so that means all of this has to be contained in the span of that one. Now, both of them are distinct and linearly independent, right? We know this is an orthogonal set. So they're linearly independent, they have the same size, and we know one span is contained in the other. By dimensionality, we know they actually have to be equal. They couldn't not be equal. If they were not equal, I could extend this set to a larger linearly independent set contained within it, which I can't possibly do. So, boom, proof's done. So, like I said, the proof of this very famous result is actually kind of easy. It's really not a hard proof at all. It's just a nice little induction. It's not a terrible proof. But now it is worth noting, the way I stated it is probably not the way you've seen it. It's definitely the way your book presents it. The way that you have probably encountered this book, if you have, is sort of in an algorithmic fashion. So it's worth stressing that the proof we just did actually tells us how to perform the Gram-Schmidt process. So, for example, let's take a set out of R3 and let's perform Gram-Schmidt to it. So we're going to take this set of linearly independent vectors, create an orthogonal set of vectors with the exact same span. So in this case, we're going to take our basis and transmorph it into a orthogonal basis. Okay. So let's label these three vectors just to make all the computations nice and easy. So we'll let x1, x2, and x3 be as follows. So the Gram-Schmidt process is as follows. W1 will just be x1, right? So the base case that we did. The next step would be do that perpendicular maneuver, that summation. Now, in this case, p is equal to 1, so the summation is not too difficult. So set up those dot products, work it out. This is guaranteed to be perpendicular to W1 by its construction. And furthermore, we know by the proof of the Gram-Schmidt process that this will have the same span as the first two vectors. And you can double check that that's indeed true. And then now if I want to compute w sub 3, what do? Well, do that perpendicular process, but now we have two summations. And now if you've ever done the Gram-Schmidt before or seen it, now you see it in all of its putrescence. Right, yeah, I'm never going to make you do anything beyond 3 by hand. It's tiresome. Alright, so there you go. the Gram-Schmidt process. The proof actually tells you exactly what you need to do. You keep extending by, well, go to the next one and do the summation. So the book has the algorithm a little bit more explicitly written, but here you go. Nice. All right. Now, it turns out that we can streamline the calculations here a little bit. But we have to introduce another idea. And so we're going to wrap things up here with another term with the word ortho involved in it. So a set of vectors is said to be orthonormal if it's orthogonal, and each one of them is a unit vector, meaning that the norm is 1. Okay, so orthogonal, again, is the fancy math term for perpendicular things. And like I mentioned, I'm not a fan of the word. I like perpendicular better. The reason I like perpendicular better is because orthonormal ruined me. So in one of my linear algebra classes, my graduate one, we were spending a lot of time talking about orthonormal stuff. And orthonormal, I got into the habit of instead of saying orthogonal, I started saying orthogonal, because, as you know, my speech is very flawed. So I got into the habit of calling orthogonal sets orthogonal, and I said that out loud in class once, and the professor was very unhappy about that. And so the lesson there is to never participate. But anyway, so yeah, so orthogonal, I always have to like pause and make sure I say it correctly, because if I'm too excited, I'll start saying orthogonal, and I don't want to live that shame again. All right. So it turns out that orthonormal are better in a few senses. So one thing to note is that, like I've already said, when you're using mathematical software to do linear algebra for you, some of them already have kind of these built-in things that they automatically do. So something I mentioned with eigenvectors is that, for example, MATLAB will automatically normalize your vectors. They'll make them be unit vectors. And there's a very good reason for that, as we're about to see. Unit vectors, in terms of computations, are a lot smoother. So the big one is the following. Let's say we do have an orthonormal set. So you are orthogonal, and all of your vectors have norm 1. Then any element in the span can be quickly and concisely written as a linear combination, because the coefficients you need to form the linear combination are just the dot products of x with u sub k. So think about it before. Normally, when I want to take a vector and figure out the linear combos based on the vectors, I'm going to have to set up a matrix and solve that. Here, you just do dot products. A lot more efficient and quicker. So when it comes to like doing hardcore numerical computations with vectors, you actually want orthonormal, because, right, as we can see right here, usually it's a lot speedier to do the computations. So let's actually prove this. This is a neat proof. So because it's in the span, we know it's a linear combination of things. So what do we want to prove? We want to prove that the scalars are the dot products of x with the vectors coming out of the orthonormal set. So fix a j and do the dot product. The dot product of u sub j and k is 0 when k is not equal to j. And when they are the same, the dot product is equal to 1. So here we're pulling that same trick. Let's dot a summation by a thing that's orthogonal to everything. So it's going to delete everything, get rid of the summation. And now we're going to go a step further. The thing it leaves over, it's just 1. And, ooh, look at that. So there we go. There's the proof. And now we see, again, there's a real power to orthogonal stuff, because it lets you deal with linear algebra and basically get rid of all the sigma notation stuff that you have to deal with. And orthonormal just goes a little extra step further. It's like, well, the thing it leaves over, that's 1. So it's even better. All right. So it's worth noting, actually, that the Gram-Schmidt process can be done orthonormally. And all you have to do is just scale out by the norm of the vectors at every step. So let me just show you how to do that, and that will wrap up the story for today. Okay, so yeah, let's take these three vectors out of R3. There they go. So the normal Gram-Schmidt process would say start off with x1, but the orthogonal one is the orthonormal one is divide out by the norm of x1 as well. Well, here x1 was nice, the norm was 1, so it doesn't do anything different. So the first step is basically the same. Now for the second step, you do the normal Gram-Schmidt, but now note, I didn't include the dot product of u1 in the bottom there because I already know that's going to equal 1. So, as we see here, orthonormal Gram-Schmidt actually goes a little bit more smoother. There's a little less computation you have to do. So, when you're doing Gram-Schmidt, you actually usually don't do it orthogonally. I was just going to say orthogonally. Ugh. You don't do it orthogonally. You do it orthonormally because it's less things to compute and we're lazy. Okay, so you do that and get your W2, but now here your W2 does not have norm 1, it has norm root 2. So when you divide it out, you get this. Now, this is kind of the one drawback, is that orthonormal, even though it is very nice, unit vectors usually have garbage inside of them that involve roots and decimals and things like that. So that is a minor drawback, but you know, there are worse things in the world. Alright, so that's how we get the U2, and then to get the U3, well, you do the same computations, and again, note here, we don't need the U1.U1, we don't need the U2.U2, and then we divide out by the norm in the end, and there's orthonormal Gram-Schmidt. And that's it. Cool stuff. So there you go. So nice. So we got a nice little coalescing of a bunch of ideas that we've discussed so far. So nice. Yeah, and here we're flirting with the geometry that's inherent in vector spaces. That sounds kind of nice. All right. Well, that's it for today. I hope you liked it, and I'll see you next time.